Welcome to this presentation on optimization methods. Optimization is the process of finding the best solution among all possible options. It's essential in numerous fields, helping us improve efficiency, enhance outcomes, and make better decisions regarding resource management. An optimization problem typically consists of an objective function that we aim to maximize or minimize, variables that influence the outcome, and possibly constraints that limit the solutions. The feasible region represents all possible solutions that satisfy these constraints. Optimization problems can be categorized in several ways. Linear problems have objective functions and constraints that are linear, while nonlinear problems involve at least one nonlinear function. Constrained problems require solutions to meet specific conditions, whereas unconstrained problems have no such limitations. In continuous optimization, variables can assume any value within a range, while discrete optimization deals with variables that take specific values. Let's look at some real-world examples. In engineering, we might minimize material usage in a bridge design while ensuring it remains strong. In economics, optimization helps in allocating resources to maximize returns on investment. In machine learning, we adjust algorithm parameters to reduce prediction errors. In logistics, finding the shortest delivery routes saves both time and fuel. Optimization enhances efficiency and effectiveness across various processes. It supports informed decision-making and drives innovation, providing a competitive advantage. Additionally, it facilitates problem-solving in complex systems by identifying the most effective solutions. With a grasp of basic optimization concepts, we're ready to explore particle swarm optimization, or PSO. PSO is a powerful technique inspired by the collective behavior of swarms in nature. It's particularly effective for solving complex, nonlinear, and multidimensional problems. Now, let's delve into particle swarm optimization, or PSO. PSO is a powerful optimization technique inspired by the social behavior observed in nature, such as bird flocking and fish schooling. Particle swarm optimization is defined as a population-based stochastic optimization technique inspired by the social behavior of bird flocking or fish schooling. It was developed by Dr. James Kennedy and Dr. Russell Eberhart in 1995. PSO has several key characteristics. It's population-based, meaning it uses a group of potential solutions called particles. It's stochastic, incorporating randomness to effectively explore the search space. And it's nature-inspired, mimicking the intelligence found in natural swarms. In a population-based approach, PSO operates with a swarm of particles. Each particle represents a potential solution to the problem. The collective behavior of these particles leads to an efficient search of the solution space. The stochastic nature of PSO means it incorporates randomness into the particles' movements. This randomness prevents premature convergence on local optima and enhances the exploration of the search space, balancing exploration and exploitation. PSO is inspired by nature, mimicking the social behavior of animals like birds and fish. Swarm intelligence arises from the collective interactions of individuals, leading to efficient problem-solving and improved performance. In PSO, particles communicate and adjust their positions based on their neighbors, similar to how birds in a flock adjust their flight paths. This information sharing enhances learning, and the collective movement leads particles towards better solutions. Compared to traditional optimization methods, PSO does not require gradient information, making it suitable for complex, nonlinear problems. It is also simpler to implement and requires tuning of fewer parameters. PSO is widely used across various fields. In engineering, it's applied for design optimization. In machine learning, it's used for training models. Robotics and control systems use PSO for path planning, and it's also employed in financial modeling and forecasting. PSO offers several advantages. It has efficient global search capabilities and is robust against getting trapped in local optima. The algorithm is easy to understand and implement, and it is flexible enough to handle a wide range of problem types. However, PSO also has some limitations. It may require careful parameter tuning to perform optimally. In complex search spaces, It can converge prematurely. Additionally, its performance can vary depending on the specific characteristics of the problem. In summary, particle swarm optimization is a nature-inspired, population-based optimization technique that utilizes randomness and social interactions among particles. It's effective for solving a wide range of optimization problems. Throughout history, nature has inspired countless innovations. The complex behaviors observed in the natural world often provide elegant solutions to challenging problems. Particle swarm optimization is one such example, drawing inspiration from the collective movement of animals. Many species exhibit remarkable collective behaviors that enhance their survival. These group dynamics are driven by simple rules followed by individuals, leading to sophisticated outcomes. Central to this is the sharing of information among group members. Let's look at birds flocking. Each bird adjusts its path based on the positions and velocities of its neighbors, without any central leader. This coordination allows the flock to move efficiently, reducing energy expenditure and enhancing protection from predators. Similarly, schooling fish align their movements with nearby individuals. This synchrony creates a dynamic that helps the school evade predators. The complex patterns we observe arise from simple behavioral rules followed by each fish. In both examples, social sharing of information is crucial. Individuals learn from the group and adjust their behavior accordingly. This information exchange leads to better decision-making and the emergence of collective intelligence. Emergent behavior refers to complex patterns arising from simple interactions among individuals. Remarkably, these sophisticated group behaviors occur without any central control, allowing the group to adapt quickly to changing environments. In particle swarm optimization, these natural principles are applied to computational algorithms. Particles represent individual animals, and through communication, they share information about potential solutions. This leads to a collective movement towards optimal solutions. Each particle explores the search space independently, but group knowledge guides the swarm towards promising regions. This balance between individual exploration and group exploitation is key to the effectiveness of PSO. Nature-inspired algorithms like PSO offer several advantages. They are robust and adaptable, able to handle dynamic changes. Their design is often simple yet powerful, making them effective for solving complex optimization problems. This visualization illustrates how particles in a swarm move through the search space. Each particle adjusts its trajectory based on personal experience and social information from neighbors. Over time, they converge towards optimal regions, showcasing dynamic interactions within the swarm. By observing natural behaviors, we can find solutions to complex technical challenges. Particle swarm optimization serves as a bridge between biology and computational intelligence, demonstrating how inspiration from nature leads to technological innovation. In summary, particle swarm optimization is deeply rooted in the natural behaviors of swarms. The key concepts of social sharing of information and emergent behavior are fundamental to its design. Nature-inspired algorithms like PSO are powerful tools for solving complex optimization problems. Now that we understand the natural inspiration behind particle swarm optimization, let's move forward to explore the fundamental concepts and mechanisms that drive the algorithm. In this section, we'll explore the fundamental concepts of particle swarm optimization. We'll define key terms and understand their roles within the algorithm, setting a solid foundation for how PSO operates. A particle in PSO is the basic unit of the algorithm. It represents a potential solution to the optimization problem and is depicted as a point within the search space. Each particle has a position and a velocity, which it uses to navigate through the space. The swarm is the collective group of all particles in the PSO algorithm. These particles work together, sharing information to explore the solution space efficiently. Swarm intelligence arises from the interactions among particles, leading to effective problem-solving. Each particle has a position, denoted as X, which represents its current location in the search space. It also has a velocity, denoted as V, indicating how its position changes over time. The new position is calculated by adding the new velocity to the current position. In simple terms, the particle moves through the space based on its velocity. The personal best, or P-best, is the best position that a particle has found individually. This value is updated whenever the particle discovers a position with a better fitness value. The personal best guides the particle's future movements toward more promising areas. The global best, or G-best, is the best position discovered by any particle in the swarm. It represents the best-known solution at any given time and influences the movement of all particles, guiding the swarm toward optimal solutions. The fitness function evaluates each particle's position by assigning a fitness value, which quantifies how close the solution is to the optimal. The objective can be either to maximize or minimize this value, depending on the problem. The fitness function guides the particles in their search for the best solutions. Particles move by adjusting their velocities, taking into account their personal best positions and the global best position. This movement is influenced by cognitive components, individual knowledge, and social components, swarm knowledge, along with random factors to enhance exploration of the search space. The cognitive component represents the particle's own experience, encouraging it to return to its personal best position. The social component reflects the swarm's collective experience, pulling the particle toward the global best position. Balancing these influences helps the swarm efficiently converge toward optimal solutions. The inertia weight, denoted as W, controls how much of the previous velocity influences the current velocity. A higher inertia weight encourages exploration of the search space, while a lower inertia weight promotes exploitation of known good areas. Adjusting inertia weight helps balance the search process. The velocity of a particle is updated using this equation. The new velocity is calculated by multiplying the inertia weight, W, with the current velocity, then adding the cognitive component, C1, times a random number, R1, times the difference between the personal best and current position, and the social component, C2, times a random number, R2, times the difference between the global best and current position. This equation incorporates the particle's momentum, personal experience, and social influence. After updating the velocity, the particle's new position is calculated by simply adding the new velocity to the current position. This step moves the particle through the search space based on its updated velocity. The acceleration coefficients C1 and C2 determine the influence of the cognitive and social components, respectively. They weigh how much the particle is pulled toward its personal best and the global best. Selecting appropriate values for these coefficients is important for the algorithm's performance. The random numbers R1 and R2 introduce stochastic behavior into the particle's movement. They are generated randomly between 0 and 1 for each particle, dimension, and iteration. This randomness prevents particles from converging too quickly and helps in exploring the search space more thoroughly. To recap, particles in PSO represent potential solutions, and the swarm is the collective group of these particles. Each particle's position and velocity determine how it moves through the search space. Personal and global best positions guide the optimization process, while the fitness function evaluates how good each solution is. The parameters W, C1, C2, R1, and R2 influence the particle's behavior and the overall performance of the algorithm. With a solid understanding of the fundamental concepts, we're now ready to delve into how particle swarm optimization utilizes these components in practice. We'll examine the algorithm's workflow and see how it solves optimization problems. In this section, we'll explore how particle swarm optimization operates. We'll provide an overview of the algorithm's main steps, giving you a clear roadmap of how PSO finds optimal solutions. The first step is initialization. We start by randomly assigning positions to each particle within the search space. Similarly, we assign random velocities to the particles. Each particle's initial personal best position, denoted as P-best, is set to its initial position. We then determine the global best position, G-best, which is the best P-best among all particles. This diagram visualizes the initialization step. Here, particles are scattered randomly throughout the search space, each with its own position and velocity. This randomness ensures that particles explore different regions of the space from the very beginning. In the evaluation step, we compute the fitness value for each particle's current position using the fitness function defined for our optimization problem. This fitness value tells us how good each particle's solution is, indicating how close it is to the optimal solution. The fitness function is a crucial component of PSO. It's a mathematical function that represents the objective of the optimization problem. Depending on our goal, it can be designed to minimize or maximize a specific criterion, such as cost, error, or efficiency. This function evaluates each particle's solution, guiding the swarm toward optimal results. Next, we update the personal best positions, or PBests. For each particle, we compare its current fitness value with the fitness of its personal best position. If the current fitness is better, we update the particle's PBest to its current position. This ensures that each particle keeps track of the best solution it has found so far. After updating the personal bests, we determine the global best position, or GBest. We identify the particle with the best fitness value among all particles. If this value is better than the current GBest fitness, we update GBest to this particle's current position. The global best serves as a guide for the entire swarm, influencing the movement of all particles toward optimal solutions. This diagram illustrates how particles update their personal bests and how the global best is determined. Particles that have found better positions update their PBests. If any particle's PBest is better than the current GBest, we update the GBest accordingly. This visual helps us understand how individual and collective learning occurs in the swarm. In the velocity update step, we adjust each particle's velocity using the velocity update equation. The new velocity is calculated by multiplying the inertia weight W by the current velocity, adding the cognitive component C1 times R1 times the difference between PBest and the current position, and adding the social component C2 times R2 times the difference between GBest and the current position. This equation combines the particle's own experience, the swarm's experience, and some randomness to guide movement. Let's break down the components of the velocity update equation. The inertia component, W times V current, maintains the particle's momentum. The cognitive component, C1 times R1 times the difference between PBest and X current, pulls the particle toward its personal best position. The social component, C2 times R2 times the difference between GBest and X current, pulls the particle toward the global best position. Random factors R1 and R2 introduce variability, aiding in exploration. After updating velocities, we update each particle's position using the position update equation. The new position is simply the current position plus the new velocity. This means particles move through the search space, guided by their updated velocities influenced by their own and the swarm's best experiences. This diagram visualizes how particles move to new positions after their velocities have been updated. The arrows indicate the direction and magnitude of each particle's movement. You can see how the particles are influenced by both their personal best positions and the global best position, converging toward optimal solutions. We repeat the evaluation, updating of personal and global bests, and updating velocities and positions until a stopping criterion is met. Common criteria include reaching a maximum number of iterations, achieving a desired fitness level, or observing no significant improvement over several iterations. Once the stopping criterion is met, the algorithm terminates, and we return the global best position as the optimal solution. This flowchart summarizes the entire PSO algorithm. We begin by initializing the particles, then enter a loop where we evaluate fitness, update personal and global bests, and adjust velocities and positions. We continue this loop until our stopping criteria are met. The flowchart provides a visual representation of the algorithm's iterative nature. Several key parameters influence the behavior of PSO. The inertia weight, W, controls how much the previous velocity affects the current one. The cognitive coefficient C1 weighs the particle's personal experience, while the social coefficient C2 weighs the swarm's influence. Random factors R1 and R2 introduce stochasticity. The population size determines the number of particles exploring the search space, and the maximum number of iterations sets a limit on the algorithm's runtime. Balancing these parameters is essential for the success of PSO. The parameters must be set to achieve a balance between exploration, which involves searching new areas, and exploitation, which focuses on refining known good areas. Common settings include setting the inertia weight, W, between 0.4 and 0.9, and both cognitive and social coefficients C1 and C2 to 2.0. However, these values may need tuning based on the specific problem at hand. Now that we've explored the fundamentals of particle swarm optimization, let's see how it performs on a real-world problem. We'll apply PSO to minimize the rastrogen function, a well-known benchmark in optimization. The rastrogen function is a standard test function used in optimization. It's known for its large search space filled with many local minima, which makes it particularly challenging. This function is widely used to evaluate and compare the performance of different optimization algorithms. Mathematically, the rastrogen function is defined as f of x equals 10 times n plus the sum from I equals 1 to n of open bracket x I squared minus 10 times cosine of 2 pi x I close bracket. In this equation, n represents the number of dimensions, and xi is the ith component of the position vector x. This 3D surface plot illustrates the rastrogen function in 2 dimensions. You can see a complex landscape with numerous peaks and valleys, representing the many local minima that can trap optimization algorithms. This visualization helps us understand the challenges involved in minimizing this function. The rastrogen function has some key characteristics. The global minimum is located at x equals 0, where the function value f of x is 0. The search domain for each variable xi is from negative 5.12 to positive 5.12. Being a multimodal function, it contains many local minima, which increases the difficulty of finding the global minimum. We choose the rastrogen function because it provides a challenging test for optimization algorithms due to its numerous local minima. It's an excellent way to demonstrate the effectiveness of particle swarm optimization in navigating complex search spaces. Moreover, it's a widely recognized benchmark for comparing algorithm performance. Our problem is to minimize the rastrogen function f of x. We aim to find the vector x that yields the lowest possible function value. The constraints are that each variable xi must lie within the range of negative 5.12 to positive 5.12. To set up the optimization problem, we'll first determine the dimensionality n, which defines the number of variables. We'll then initialize a swarm of particles, positioning them randomly within the defined search space. Finally, we'll apply particle swarm optimization to search for the global minimum of the function. The number of dimensions n significantly impacts the problem's complexity. More dimensions mean a larger search space and more variables to optimize. For this example, we'll use n equals 2, which allows us to visualize the problem in 2 dimensions. Minimizing the rastrogen function is challenging because of the numerous local minima that can trap optimization algorithms. Effective exploration of the search space is essential to avoid these traps. Achieving a balance between exploration and exploitation is crucial for finding the global minimum. Particle swarm optimization is well suited for this problem. Its stochastic nature helps particles escape local minima, and the swarm intelligence enables a comprehensive search of the space. Additionally, we can tune PSO's parameters to better handle complex landscapes like that of the rastrogen function. Through this example, we aim to demonstrate PSO's ability to find the global minimum of the rastrogen function. We'll observe how the swarm converges over iterations and how effectively PSO navigates the complex search space. We anticipate visualizing the optimization process by showing particles moving through the search space, converging toward the global minimum at the origin. We'll also track changes in fitness values over time to illustrate the improvement in solutions. Before we implement PSO, we'll define parameter values suitable for this problem, such as the number of particles, inertia weight, and acceleration coefficients. We'll set up the algorithm respecting the problem constraints and get ready to execute PSO to observe the results. To summarize, our objective is to minimize the rastrogen function, a challenging task due to its multiple local minima. Particle swarm optimization, with its ability to balance exploration and exploitation, is an effective method for tackling this problem. Let's clearly define our optimization task. Our goal is to minimize the function f of x, where x is a vector in n-dimensional real space. For visualization purposes, we'll consider n equals 2, though particle swarm optimization can handle higher dimensions. The constraint is that each variable xi must be within the range of -5.12 to +5.12. Now that we've formulated our problem, let's explore how particle swarm optimization can help us find the global minimum of the rastrogen function. Let's delve into how we can implement PSO to minimize the rastrogen function. We'll outline the algorithm setup and the steps we'll follow. We'll use a swarm of 30 particles. The inertia weight W is set to 0.7, balancing the influence of previous velocities. Both the cognitive coefficient C1 and the social coefficient C2 are set to 1.5, giving equal importance to personal experience and social influence. Each particle's position is randomly initialized within the range of -5.12 to +5.12. Velocities are also randomly assigned within acceptable bounds. Initially, each particle's personal best position is set to its starting position. We evaluate the fitness of each particle by computing the rastrogen function at its current position. This fitness value shows how close the particle is to the global minimum. We then update each particle's personal best and the swarm's global best accordingly. The algorithm will terminate when it reaches a maximum of 1,000 iterations or when the fitness value f of x falls below 0.01. Meeting either condition signifies a satisfactory solution has been found. Now, let's observe how PSO performs over iterations and how particles converge toward the global minimum. This graph illustrates the decrease in the global best fitness value over iterations. We notice a rapid initial improvement, followed by gradual convergence as the particles fine-tune their search. These plots show the positions of particles at various iterations. Initially scattered, the particles progressively move closer to the global minimum at the origin. We observe that the swarm exhibits rapid improvement at the start, thanks to broad exploration. Over time, particles begin to exploit areas with better fitness, leading to gradual convergence and clustering near the global minimum. The initial diversity in particle positions helps prevent premature convergence to local minima. As particles share information about their personal bests and the global best, they collectively move toward the optimal solution. Our parameter choices are key to achieving this balance. Finally, let's analyze the results of our PSO implementation and discuss the insights gained. The PSO algorithm identified a global best position at x equals 0.002 minus 0.001, with a fitness value of f of x equals 0.0005. This is remarkably close to the theoretical global minimum. The algorithm effectively converged to a solution near the global minimum, doing so efficiently within our iteration limit. This demonstrates PSO's robustness in handling complex optimization problems with multiple local minima. The balance between exploration and exploitation was key to the effective optimization. The swarm made rapid initial progress, then fine-tuned its search in later iterations. Our parameter settings played a significant role in this successful convergence. When compared to other optimization methods such as genetic algorithms, PSO shows favorable performance. It offers a simpler implementation with fewer parameters to adjust and is effective at avoiding traps in local minima due to its stochastic nature and social sharing mechanisms. In conclusion, particle swarm optimization effectively minimized the rastrogen function, validating its power as an optimization tool for complex tasks. It demonstrated the capability to navigate challenging search spaces and find near-optimal solutions efficiently. Now, let's explore how particle swarm optimization is applied in various real-world scenarios. PSO's versatility and adaptability make it a valuable tool across numerous industries. In engineering design, PSO is used to optimize structural components, balancing factors like weight and strength to achieve efficient designs. It's also applied in designing aerodynamic shapes for cars and aircraft, where optimizing for minimal drag and maximal stability is crucial. Additionally, PSO aids in improving thermal systems by finding optimal configurations for heat exchangers and cooling systems. In the realm of neural networks and machine learning, PSO assists in training models by optimizing weights and biases, leading to better performance and accuracy. It is also employed in hyperparameter optimization, where selecting the right parameters significantly impacts the model's effectiveness. Moreover, PSO helps in feature selection and dimensionality reduction, enhancing model efficiency and interpretability. In robotics, PSO is used for the coordinated control of swarm robots, enabling them to work together to accomplish tasks like area coverage, search and rescue, and environmental monitoring. It also aids in path planning and obstacle avoidance, ensuring robots navigate efficiently and safely. Additionally, PSO optimizes control parameters for robotic manipulators, improving precision and responsiveness. In energy systems, PSO plays a role in load forecasting, helping utilities predict energy demand and distribute power efficiently. It optimizes power grid operations by reducing transmission losses and improving stability. PSO is also used in scheduling renewable energy sources like wind and solar, balancing supply and demand while maximizing resource utilization. In telecommunications, PSO optimizes network routing to minimize latency and ensure reliable data transmission. It assists in bandwidth allocation, maximizing network throughput and quality of service. PSO is also involved in designing efficient communication protocols that adapt to changing network conditions. In the financial sector, PSO is applied to portfolio optimization, helping investors balance risk and return by selecting an optimal mix of assets. It aids in risk assessment and management by modeling complex financial systems. PSO is also used in predictive modeling to analyze market trends and inform investment strategies. In healthcare, PSO optimizes treatment plans in radiation therapy by calculating the best angles and intensities to target tumors while minimizing damage to healthy tissue. It assists in medical image processing, enhancing image quality for better diagnosis. PSO is also used in drug discovery, optimizing molecular structures for effective therapeutic compounds. PSO contributes to environmental science by modeling ecological systems, aiding in conservation efforts. It optimizes resource allocation in environmental management, ensuring sustainable use of natural resources. PSO is also used to predict pollution dispersion and climate patterns, supporting efforts to mitigate environmental impacts. In summary, particle swarm optimization is a versatile tool that adapts to a wide range of complex optimization problems across different industries. Its simplicity and ease of implementation make it accessible and practical. As challenges evolve, PSO continues to expand into new fields, driving innovation and efficiency. As we conclude this presentation, let's recap the key takeaways. We explored particle swarm optimization, PSO, a powerful optimization technique inspired by the social behavior of swarms in nature. We delved into its core components, including particles representing potential solutions, velocities and positions guiding their movement, and the concepts of personal bests and global bests that steer the swarm toward optimal solutions. We examined how PSO's algorithm mechanics balance exploration and exploitation through iterative updates influenced by cognitive and social components. PSO has proven effective in a wide range of applications, from engineering design and machine learning to robotics, energy systems, telecommunications, and finance. Its advantages include simple implementation, few parameters to adjust, and robustness in navigating complex search spaces filled with local minima. Thank you all for your attention and participation throughout this presentation. I hope it has been informative and has sparked your interest in particle swarm optimization.